Hi everyone. If you like the way I teach and want me to be your teacher, the link to my engineering fundamental school is in the description below. Enjoy the video. In the last video, we spoke about vector addition, and that could be summarized by the picture on your screen. I reminded you of the parallelogram rule of vector addition, and we also went through an example where we broke a vector into components, which are not orthogonal, and we used things like the sine rule and the cosine rule. Though that method is good for breaking a vector down into components when your directions are not orthogonal, if we have multiple vectors that we need to add, we're not going to keep drawing triangles over and over and then keep on using the sine and cosine rule. It's not ideal and it takes way too much time. Instead, what we do is we place down a Cartesian coordinate system and project vectors onto that axis. The idea of projection is closely related to the dot product. So in this video, what we'll be doing is we'll be reviewing the dot product. The dot product is an absolutely critical idea for the rest of this course and some other courses in the engineering curriculum. And I would really recommend you to pay close attention to this video because this concept is going to be reused repeatedly. Let's say we have a vector b and a vector a. What does it mean to take the dot product of vector b with vector a? Essentially, what it is it's as if we took a flashlight. We take this flashlight and shine it down. Note that the flashlight is perpendicular to the A direction. Once we turn this flashlight on, B will cast a shadow in the direction of A, and we'll end up with this length right here. This length is, if this angle is theta, this length is B cosine theta. And if we scale up this component that we find by the length of vector A, what we'll get is the dot product is A B cosine theta. So there's two ideas really in the dot product. The idea of projection and also the idea of scaling. What happens if instead we did A dotted with B? Well, again, we would have that flashlight. As you can see, the flashlight here would be perpendicular to the B direction. We would shine that light. The shadow casted by A in the B direction has a length, which is A cosine theta, and we scale it up by the length of B. So again, we get A B cosine theta. The projection component would be this A cosine theta, and the scaling component would be this, the length of B. How can we go about isolating just the projection component of this? All we would have to do is make that scaling factor. We want the scaling factor equal to 1, or we want to take the dot product with a unit vector. Let's say we had another scenario. Let's say we had another scenario where we had a vector b. The length of b is not equal to 1, and then we have a vector a, where the vector a is exactly equal to I hat. Let's just draw this I hat here. If we took the dot product of B with I hat, what we'd be doing is finding the component of B in the direction of I hat, which would be equal to B cosine theta. And we scale it up by the unit vector length, which is just 1. So the magnitude wouldn't change of this scalar. Note that the dot product of two vectors is a scalar. Another case we can look at is if A and B are perpendicular. Let's say we have this vector here, vector A, and the vector here, vector B. Now, of course, if we took the dot product of this vector A and B, the component of A pointing in the direction of B, shining down this flashlight here, if we shone this flashlight down, the component of A pointing in the direction of B would just be a dot. And the length of a dot is equal to 0. We scale up 0 by the length of B, it's still 0. So the dot product of perpendicular vectors is equal to 0. And two more important facts about the dot products. A dotted with B is going to be greater than 0 if the absolute value of theta is less than 90 degrees. And A dotted with B is going to be less than 0 if the absolute value of theta is greater than 90 degrees. So if they're generally pointing in the same direction, they'll have a positive dot product. If they're pointing in opposite directions, they'll have a negative dot product. Now, what you might be wondering is, how does this relate to statics? Let me show you. This picture is going to say everything. If we have a force, F1, and another force, F2, and we know the angles, we wanted to find the resultant force, or the sum of the forces, F, which is this force. All we would do is we would use that parallelogram rule of vector addition, where we place F2 on the head of F1, and instead of using the sine and cosine rule, we're going to use this idea of projection. We have our flashlight above, and we're going to find the component of F1 pointing in the x direction by taking its dot product with the unit vector pointing in the x direction, which is I hat. This would be F1x. The F2x is the same thing, F2 projected onto the x-axis, shown right here, F2x. Their sum is going to be the total x component of the resultant force, Fx. If we write out exactly what we just said, the sum of the forces has to be equal to the sum of the vectors F1 and F2. What we spoke about just now is simply the equation only for the x-axis. Basically what we did is we projected the equation in the I hat direction by taking its dot product with I hat. What is I hat dotted with F1 and I hat dotted with F2? This is essentially equal to I hat dotted with F is the sum of the forces in the x direction. I hat dotted with F1 is equal to F1x, and I hat dotted with F2 is F2x. So this is a scalar equation. We can also write this equation for our projection in the y-axis by dotting with J. If we dotted that above equation with J, what we will get is that the sum of the forces in the y direction is equal to F2y. plus F1y. And again, this is a scalar equation. How do we find this F1x or F2x or any of the other components that we were speaking about? It all breaks down into right triangles. If we have a force F1 and we wish to find its x components and its y components, let's say it's at an angle theta, the sine of theta is equal to the opposite side divided by the hypotenuse, F1. So we know that this opposite side is going to be equal to F1 sine of theta. If we ever see an opposite side, we can just write the magnitude multiplied by sine of theta. What about the adjacent side? We can do the same thing. The adjacent side will just be equal to F1 cosine of theta. Let's do an example and bring it all together. Shown here is our example. What we have is 3 different forces, and what we wish to find is the resultant force. So the overall question is find the total force, or the sum of the forces in the above system. How are we going to do it? Let's write down our equation. The sum of the forces is the sum of all of the forces shown above. The first force, the second force, and the third force. What we can do is project this equation in 2 directions. Let's start off with the I hat projection. The sum of the forces in the x direction has to be equal to F1x plus F2x plus F3x. What is F1x equal to? Let's label the forces above. Let's call this one F1. Let's call this one F2. Let's call this one F3. F1x is the component of F1 pointing in the x direction, which is 10 cosine of 30 degrees. F2x, which is negative since it's pointing leftward, its dot product with I hats is negative because they're pointing in generally different directions. It's negative 20 cosine of 20 degrees. And lastly, we have plus 30 sine of 30 degrees. That comes out to be 4.866 newtons. What if we projected it in the y direction by dotting with the unit vector j hat? We would get that the sum of the forces in the y direction is equal to F1y plus F2y plus F3y. That's going to be equal to 10 sine of 30 degrees plus 20 sine of 20 degrees plus 30 cosine of 30 degrees. That total comes out to be 37.82 newtons. Our total force vector can be described by the sum of the forces in the x direction, which is 4.866 in the I, plus 37.82 in the j newtons. This is our final answer. I hope this video was a good review of the dot product and showed its utility. I hope to see you in the next video. Keep learning and keep working hard. Goodbye.